I shall continue with the topic on band structure. So let me go back to the idea of an atom again. If you think of an atom as having a proton with a number of different orbits with different energy levels around it, and in general for heavier atoms that have more electrons than hydrogen, there would be many more than one or two electrons around it. And for the materials that we see around us in everyday life, that we see and touch, like metals and plastics and wood and so on, these are often atoms like iron, oxygen, carbon, etc., that would often have maybe at least 2 or 3 shells or even more, as in orbits of electrons around inside the atoms that are filled with electrons. So what we would often do when we talk about band structures is to think in terms of the energy levels. So I've drawn these lines before when I talked about the hydrogen atom, where we imagine that a vertical axis of energy, and where, for example, the lowest level would represent the innermost orbits that has the lowest energy, and then we can imagine maybe drawing a circle or two at each line to represent the electrons at that energy level. So for example, that line there would represent the energy of the innermost orbit, and the two little circles there would represent the there are these 2 electrons in the innermost orbit at the lowest energy level. And the next one up might correspond to the next orbit, and there might be more electrons. Right, in the normal atoms, there would usually be up to 8 electrons in this second level. And then if this atom has more electrons, then there might be more electrons. There might be electrons in the third level, and so on. So we could think about the energy levels in the diagram using such so-called energy level diagrams. And in the case of a single atom, we are already quite familiar with the hydrogen atom, which has a number of energy levels, and we have even looked at the energies and the emission spectrum quite a bit. Now, for the more common atoms that we see or that we touch or feel every day, things are more complicated. The energy levels, there might be a lot more complicated energy levels with a lot more electrons in them. But I'm going to skip right over this and look at something even more complicated. Look at what happens when I have lots of atoms in a solid that are touching each other. So let's think of an example. Let's say I have a piece of solid material. Okay, what kind of solid material can we think about? We would probably want to think of I'll be looking at ideas about conductors and insulators of electricity. So let's think about an example each. A conductor would be, say, copper. So that's a conductor. An insulator would be what's an insulator? Maybe say phosphorus. Okay, and something in between, a semiconductor. Right, that's most relevant to what I want to talk about in the coming videos. Silicon. So let's have in mind some of these examples when I look at this the energy levels of the atoms in this material. Right. So we might imagine that in this material, in this solid, okay, I'm talking about solid here, there are lots and lots of atoms touching each other. Okay, all touching each other. Okay, so lots and lots of atoms like that, and in each atom there are lots and lots of electrons in the energy levels. Right. Okay, and let me draw a line. Let me just imagine drawing an imaginary line right through that solid. So this line would go through many atoms. Okay, so it's all imaginary. I mean the line. So let's just imagine a line sort of going through many atoms in the solid. Now, as a line goes through the atom, it will go through the electric field. All right, let's think about the electric field due to the positive nuclei, the positive protons in each atom. Now remember what it looks like. The electric field or potential, right? I want to think about the potential. The electric potential around each nucleus it follows the same formula as the Coulomb potential for point charge, which is this is the Coulomb potential. So if you remember, it's V is equal to minus 1 over 4 pi epsilon naught times, let's say Q is the charge of each nucleus, divided by R, where R is, let's say, the distance from the nucleus. Okay. Now if I plot a graph of this, against R, the graph looks like this. V against R. So that's what the graph looks like. Now if I imagine that there's a nucleus here at R equal to 0, as I move away from R on either side, I would expect that the potential would decrease in magnitude in the same way on both sides, because the atom is symmetrical, left or right. Okay, and the potential would be negative because right, okay, perhaps I should use the term potential energy. There shouldn't be an I there. So let me use the term potential energy, because I really want to talk about this in terms of the energy of the electrons. So if I think about the electron, let's say the charge of each electron is E, then I would have to multiply the Q by the E, and there must be a minus sign because the charges are opposite. Okay, so that's why I've drawn the two curves below the R-axis. It's negative because because they attract, opposite charges attract, so it's a negative potential for the electron. So this would be what the potential energy of an electron look like around the nucleus of each atom. That is around each one of this, right? Around each of the atoms in a solid, you will find the nucleus producing a potential energy like that for the electrons around it. So suppose that I follow this line, I call it X. I follow my line X, and I try and draw the potential energy on the electrons due to the positive nuclei of the atoms, right? That this x-axis goes through. So every time it goes through an atom or goes close to the nucleus of an atom, we would expect it to experience a potential from that atom, from that nuclei, that looks like this. So if there's an atom here, its nucleus would contribute such a potential curve, like this. Okay, should perhaps have a vertical axis. So let's say that's my V, that's my vertical axis, and that's X. So we might imagine that there is say at this position there is a nucleus of an atom, and maybe at some other position there's another nucleus, and another nucleus here as this line goes through the solid. So there would be lots of nuclei of atoms along this line. Okay, and each of these nuclei would have this Coulomb potential energy around it that would be experienced by the surrounding electrons. Okay, and so on. Right. Also, at any particular, say at a point in between, say two atoms, if an electron is in between two atoms, it will experience a total potential energy which is equal to the sum of the potential energy due to each nucleus. In other words, I can imagine adding this curve to this curve. Right? What does it mean by adding this curve to this curve? Right. So if I think of this as the axis, and these lines are these curved lines as the graph in this x-v axis, and so that's 0 there. Then if I try to add, let's say, this graph and this graph, I'll basically be adding two numbers that are given by a formula like this. So this graph would give me say a negative value here, and this graph would give me a negative value there. So if I add up those two numbers, I get an answer which is even more negative, somewhere there. So if I imagine adding this curve to this curve, I would end up with a graph that looks like this. Like this. Oops. Try again. Right, so this plus this is equal to this, maybe this plus this, as in this curve, plus this again, which is that curve, will give you a more negative number, which is there. And maybe this plus this will give you somewhere, a point somewhere there. So when we add these two graphs, we would probably get something that looks like this. Okay, and you can do it for all the space in between neighboring atoms, and we would get a similar pattern that repeats. over and over, right through the whole solid. And so on. So if an electron goes through the solid, that's pretty much what it will see, what it will experience in terms of its own potential energy. That's pretty much how its own potential energy would change. Okay. So we know that if we just have one atom, then it has definite energy levels, like we have seen for the hydrogen atom. So we could imagine that if it's just a single nucleus in a single atom, I might imagine drawing these energy levels, or sort of I can draw it over the same graph here, where that's the origin, and these lines. All right, let's say that's the 0 level. So if I put this graph onto the same graph as the potential, I might imagine getting energy levels that look like this. Okay, so these are the possible energies that an electron in the atom could occupy. So in the same way, I can do that here when I have this lots of atoms along a row. Okay, so this atom, if it is alone, if it is on its own, would have an energy level there, maybe there, maybe there, maybe there, and so on. And that one, there, 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 and so on. Right? There are lots more as it goes up towards 0. So each atom will have the same energy levels simply because, if it is on its own, simply because they are identical atoms, right? So let me draw a little more. Right, and it keeps going up. Okay, they all keep going up. So these are not the only levels. There's an infinite number of levels all the way up to 0. Okay, but as I emphasized, these are the levels if each atom is on its own, like this, on its own. Now something different happens when all the atoms are in contact or are close to each other. Something different happens. So what happens? Let's have a look. Now, imagine what happens if I have an electron here at this level. Now, if I have an electron in this level and an atom nearby, okay, then this electron is separated from that atom by this potential barrier. If you remember, I've talked quite a bit about potential barrier when I talked about tunneling in an earlier video. And you know what happens if there is a potential barrier? It is possible for this electron to, the wave of this electron to spread out into the next atom, or it spread across the barrier, because it's a wave. Wave can spread through barrier. And if that happens, that means there's actually a non-zero chance, right? There is a chance that the electron can actually be at the other atom. Now that seems very strange, but that's the result of the wave property of the electron. And if it's possible for the electron to be at the other atom, then the potential, the attraction from the nucleus of the other atom must surely affect the energy of this electron. And indeed it does. By having say 2 or more nuclei of atoms close together like this, the original energy level of the atom becomes disturbed. They becomes a bit different. right? Depending on how close they are. If they're very far apart, then it's just like the original atom when it's on its own. But if they're quite close together, we would expect that that energy level becomes different. It becomes different. Now, how different and what it exactly becomes, it's something quite complicated that I shan't go into. But what I'll just say is that if we have only two atoms, if let's say if I forget all the other atoms for now, if I have only two atoms together, then the corresponding energy levels when the two atoms are close together, right? Each energy level would actually turn into two energy levels, right? We will actually have two levels, and for those as well, right? They all have two levels, and that's the effect of the two potential sort of affecting each other. Now, if I have three atoms together, you might imagine that it would then split into three levels, right? Each one of these would split into three levels. And it's the same for all the levels. And if I have many atoms together, right, it would actually split into many levels. And if you're talking about a whole piece of solid, then the kind of number that we're talking about is the Avogadro's constant. We're talking about 6.022 times 10 to the power of 23 atoms, or that kind of magnitude. It's a huge number of atoms. So you might imagine that each of these levels would be split into a huge number of very closely spaced energy levels. So closely spaced that if I draw them, it would just look like this. You can't tell them apart even, but you can't actually tell them apart by looking at it. Right? It just looks like a band, which is in fact what it is called. And it's the same for all the atoms. Right? Each electron in the atom, right, would therefore be among one of these many Avogadro constants number of lines in each level. A huge number of lines, and so on and so on. Right? I shall not try and draw all of them. So each of this looks like a continuous spread of lines, and it is called a band or an energy band, which is why we have the name band structure. Write it down here. Band structure. Right, band because it looks like a kind of a band, a continuous, in the sense of continuous spread of energy. Structure because things can get really complicated, which I shan't go into, but I'll be looking at one or two details that are relevant to conduction, insulation, and semiconductors.